thank you for inviting me. I am coming from a little bit different angle to the CO2 issue. I'm coming from electrochemical engineering, particularly electrochemical power sources. And I will present our work at the intersection of CO2 utilization and large grid-scale energy storage. Basically, the question that I am posing, and hopefully I can develop a strong answer for it, can we make large-scale batteries utilizing carbon dioxide? So, yeah, that's good. First of all, as an introduction to the CO2 chemical utilization issue, as most of you are very familiar, the chemical utilization of CO2 is a very exciting area. Many different catalytic processes are being investigated, and one way or another, it involves combining carbon dioxide with hydrogen, hopefully green hydrogen, to produce a variety of chemicals. However, all this research, when it comes to translating it on an industrial scale, so far yielded only a few successes. And one of them is carbon dioxide conversion to methanol by Carbon Recycling International. This is a process that has been commercialized over 10 years ago and produces about 5 million liters of methanol per year. And another process that actually is not even yet totally industrial, but they are in final phases of pilot plants, a very interesting one by Covestro in Germany, producing polyurethanes from carbon dioxide. So I am sure that somewhere down the road, we will see mattresses advertised that they are produced from carbon dioxide. That's the whole idea there, through a catalytic process. But what are the challenges? As I said, from all this exciting research, turning to industrial scale? Well, of course, cost. Industry cares about the cost, 3 to 4 times more expensive producing these chemicals than through the conventional way. And another very interesting point that many times is lost, that comparative to the 40 gigaton about CO2 emissions, if the entire chemical industry would turn to be CO2 based, would still use only less than 1% of the CO2 that is being emitted globally for non-fuel use. That's what I mean. So there is lots of scope to develop different technologies, different things with carbon dioxide and to find different solutions. Now, on the other side of the coin of this energy transition business is the electrification of everything. And clearly, there is no renewable energy if there is no renewable energy storage. And batteries play an extremely important role, obviously, in this arena of large grid-scale energy storage. But when we think of batteries, we immediately think of a metal. Lithium batteries, of course, involve many other metals as well, cobalt, nickel, manganese, so on. But other type of batteries, vanadium, zinc. My point here is that it's very well known the strong dependence on the mineral and metal supply chain, the price oscillations, and price challenges that are in that area. And our thinking was kind of outside the box thinking. Can we utilize carbon dioxide in a battery solution to offer a cost-effective, competitive grid-scale energy storage option to industry? Well, what would be the reason to build a battery based on carbon dioxide? One would be the cost, because no matter how we look at the cost of CO2 capture, if we look at industrial emissions, typically between $50 to $150 per ton, orders of magnitude cheaper than any other metal. Even the cheapest metal like zinc is one of the cheapest battery metals out there, is over 10 times cheaper than zinc. And even if we think of CO2 from direct air capture, still there is a price differential and a price advantage for utilizing CO2. But the big question is, how can we make a battery out of carbon dioxide? So here is our solution, which now has been patented in over 52 countries. First, I give you just high-level overview, and then I will enter in some technical details to explain you how these batteries could work. So when the battery is charging, captured carbon dioxide is used together with electrolytes, and during the battery charge process, renewable energy is being stored by converting carbon dioxide and some components of the electrolytes into a high energy density chemical. And I will give you an example for that high energy density chemical. Now, when the battery is discharging, on one hand, we are releasing part of the stored electricity that has been stored during the charge process, but also, as I will show you, we can generate in a hybrid mode value-added chemicals, carbonates and possibly bicarbonates, which again adds value to the overall system. So our objective here is to have a high energy density battery, long duration storage at low cost. Long duration is the name of the game when it comes to grid scale energy storage. And by long duration here, we mean greater than 4 hours. Lithium-ion batteries are very good, for 1.5, 2 hours type of storage. And of course, they are also expensive. I had some metrics in a previous slide. I didn't dwell too much on those. So long duration storage at a low cost is really critical here. And I think that here we can play a very important role, and obviously long cycle life, because this type of grid scale batteries should operate up to 15 to 25 years, such that to match the lifetime of the renewable energy infrastructure. So I know this slide is a little bit out of context here. I just want to show in principle what is needed to create such a battery that I showed at high level in the previous slide. So it's very important, the so-called bifunctional catalyst here on the negative electrode that can carry out the CO2 reduction to formate. That is one example for a high energy density that can be created from CO2. And on the same catalytic surface, then, when the battery is discharging, we have two options. One is to go from this formate back to CO2, so to have a closed loop. But more interestingly, as I mentioned, if we can go from formate to carbonates at higher pHs, then I think we have a better option because we have a net CO2 sink. And the theoretical specific energy of this battery is about 3 times higher than the vanadium redox flow battery, and is inching toward the theoretical specific energy of a lithium-ion battery. Again, the way how we should look at this as a hybrid system, energy storage and a CO2 mineralization system combined together. This is a block flow diagram. We can generate carbonates or bicarbonates dependent on customer needs or how the downstream processing is being set up. So what can we do with 1 ton of CO2? If we assume an energy efficiency of about 70%, 1 ton of CO2 would release 1.6 megawatt hour of electricity. That would be enough to charge 14 Teslas, Model S's, and or to supply electricity for a day for 65 Vancouver houses. So if this scales, definitely it would contribute to the energy storage picture. And how do we see it integrated? Let's say we assume a cement plant, but there are many other hard to decarbonize industries out there. But let's just take an example, a cement plant. They have their flue gases, CO2 being captured and purified. And when the battery is charging, the CO2 is being utilized together with renewable electricity and electrolytes. And then energy is released in the discharge mode, so that can go on site. If there is surplus electricity, of course, that can go outside the grid that the plant is using. And we are generating this carbonate or bicarbonate product. And interestingly enough, sodium bicarbonate, if that's what we are generating, we could reuse it also as part of the electrolyte, but also can be used for flue gas purification. So this is one application area. And just a couple of more slides I have where we are at actually. We started obviously on a very small scale, figuring out the catalysts, the membranes and system components. Now we are on a 100 square centimeter electrode area scale with and building stacks of larger and larger sizes. This is just the data to show that we were able to scale the power density of this battery when we increased the electrode area by 10 times. And to conclude my presentation, so I presented a new type of battery that utilizes carbon dioxide, kind of combines decarbonization with energy storage. So we are addressing two exponentially growing markets with the same technology. Now we are in the process of scale up to stacks of different power output, hopefully up to 5 kilowatts, and we are looking for partnerships, collaborations for technology demonstration, and also for eventually leading to commercial deployment. And I would like to acknowledge the teams from Agora Energy, a company that I co-founded, a team at UBC, and funding both private and different government source funding. And thank you very much for your attention.